Hello everyone, this is a continuation of my previous video where I explained query, key and value vectors, why they are needed and how we get them. And this video is going to explain scaled dot product attention and self-attention mechanism overall, okay? So in the previous video we had a sentence cat sat on mat, okay? So based on that, we knew that x1 was for cat, x2 was for sat, x3 was for on, x4 was for mat. Okay, so we also had wq, which is weight matrix for q, weight matrix for k is wk, and we have wv. Okay, so x1 dot multiplied with wk gives us q1 and so on. Okay, so x4 dot multiplied with wv will give us v4. Okay, so if we had more words, we would have more q, k, v values. Okay, so we had just 4 words, that's why we have overall this many. Okay, q1 k1 v1, q2 k3 k2 v2, and so on. So after that we have to stack all these rows, stack all q rows in this q variable. So this will create a q matrix. So we have 4 q values, right? q1, q2, q3, q4, which means there are 4 rows, right? So in each row, let's say there are 64 values. Okay, so just imagine 64 values. So this will mean there are 4 rows and 64 columns, okay, for only q matrix. And it will be the same for k, it will be the same for v. So this is what I have written here. Q is shape 4 by 64, and same for k and v. And 64 is just a common choice for the qkv dimension, even if the input x was 512. So x1, x2, x3, x4, whatever their sizes were, 64 is just common. You'll see why this matters in multi-head attention later, in my later video. Okay, so now the step 2 is dot product scores part. Okay, so let's say we have q2, which is 1, 0 and 1, and I'm using 3 dimensions instead of 64 just to keep it readable. Okay, just to show you a concrete example. So we also have k1, which is 0.9, 1, 0.8, and k2, k3, k4 values. Okay, so we have to do the dot product. So q2 dot product with k1 gives us 1.7, which means cat matches well. Okay, so what does it mean? Sat is a verb which is looking for its subject and location. So cat, which came from q2 dot k1, which is 1.7, is a higher value. Why higher? Because so q2 dot multiplied with k2 is 0.3, q2 dot k3 is 0.3, q2 dot k4 is 1.6. so q2 dot k4 is 1.6. Why? Because it's about the mat. Okay, so sat is looking for its subject and location. So subject is cat and mat is its location. So that's why they are getting higher scores. Okay, they should get higher score. So that's why it makes sense. So you do this for every query row, not just for sat. Okay, so I have just shown you for q2, you have to do it for q1, q3, q4, all of them. Okay, so the compact version is like this. Scores is equal to q dot k transpose. Okay, and its shape is 4 by 4, and each entry here, let's call them ij. So how much it will mean, how much word I attends toward j. Okay, so after that, after getting all these values, we have to divide them by root over dimension. Okay, so in the example above, we talked about using the dimension 3. Okay, but usually in practice it's 64. So um, dot product is sum of demultiplications. So the more dimensions there are, which means the more numbers there are, the larger the sums get. Just by having more terms to add. So there are more numbers, more terms. And so more addition, more multiplication. That's why we get higher values. So a 64 dimension dot product naturally produces bigger numbers than 3-dimension ones, even if the individual numbers are similar in size. Okay. So big scores will create a problem in the next step. Okay, so the next step is about using the softmax function. I'll talk about it in a while, but just remember that we will have a problem, or it will create a problem if we do not divide by dimension of k. Okay, so you just have to scale them down by dividing. Okay, so let's say we divide it with root over 64. So divide it with 8, and yeah. So after division, we use the softmax function. So let's say after division, we have these values: 1.7, 0.3, 0.3, and 1.6. So we make them go through the softmax function. After that, we get roughly speaking 0.43, 0.07, 0.07, and 0.4. Okay, so you can get the actual value from your calculator if you want. Okay, this is just for making you understand this stuff. So a softmax actually takes your row of scores and turns them into weights that sum to 1. Okay, so basically adding all these values now will give you 1 as output. Okay, so higher the scores will mean higher the weights. Okay, so let's say 0.43, give 43% of your attention to cat. Okay, for 43%. Why? Because this is for cats. For 0.43, we got it earlier, right? We got 0.4 for math. Okay, so which means give 40% attention to math. Then give 7% to each of the others. Okay, so if you have already learned normalization and how it works, then you already know that you take all these numbers like 1.7, 0.3, 0.3, and 1.6. The sum will give you 3.9, and then if you divide them up, you get 0.44, 0.08, 0.08, and 0.41. And if you now add all these values, you'll get 1. Okay, so the point is, if your goal is to just get the sum 1 from the values, why not just use this sum division or normalization instead of softmax? Well, there is a problem there, because the difference is that the softmax uses e to the power x internally, okay, which basically amplifies the gap between high and low scores. So the higher scores will get even higher scores, and the lower scores will get pushed lower. Okay, this makes the model more decisive. Okay, so that's why we use softmax instead of normalization. Okay, so, and if you haven't learned normalization, just skip that part, just use softmax, that's it. Okay, and now let's talk about the saturation problem. So what is this saturation problem? Well, I have already said that you have to you have to divide by root over dimension. Okay, and if you do not do that, you'll get a problem, and that problem is the saturation problem. Okay, so in simple terms, if you want to think about it, if you give values like 42 and 38 in the softmax function, then e to the power 40 is an astronomically large number compared to e to the power 2. Okay, so the model will think, okay, so the word for e to the power 40 is basically the one to select, and just forget about the others. Okay, because the others are just having lower numbers. Okay, but the model should not do that. Okay, so that's why we divide to make things better. And there is a bigger explanation to it. I'm just reading it for you. uh, the training process works by making small adjustments to the weight matrices. Okay, so WK, Q, WK, WV. Okay, to know which direction to adjust, the model needs to measure how much does changing this number change the final error. So it needs to keep the final error as low as possible, right? The measurement is the gradient. So the result, when you have e to the power 40 for one and e to the power 2 for the other, the result is that one weight is essentially 1 and the others are essentially 0. Okay, so the output is completely flat in response to small changes in the outputs. Okay, when the output doesn't change, um, the gradient is near 0. The model stops learning. It cannot really figure out which direction to adjust. So that's basically saturation. If you haven't understood it, just forget about it. You just have to divide by root over dimension. Okay. So yeah, that's about it. And finally, you have to multiply by the value matrix. Okay, so we got the weights after the softmax function. After using it, we got 0.43, 0.07, 0.07, and 0.4. And now the output of sat is going to be equal to 0.43 dot multiplied by v1 plus 0.07 dot v2 plus 0.07 dot v3 and so on. Okay, so this is the output of sat. So what is this output vector? Well, it is the new representation of sat. Let's call it z2 if you want. Do not call it x2 anymore, because x2 was that initial vector which had 512 numbers for the word sat. Okay, so this one is just a new vector, the same length as the v vectors. Okay, 64 numbers that contains a weighted blend of content from every word. What does it mean? Well, a weighted blend is just that we are multiplying these weights with the value vectors. Okay, that's why, like 0.43 dot v1. Okay, so 0.4 dot v4. Before attention, x2 was sat, the word sat in isolation. After attention, it is z2, which is the word sat, but enriched with 43% of cat's content, 40% of mat's content, and small amounts of the rest. Okay, so this z2 is what gets passed forward to the next part of the transformer layer, or you can say for the next iteration, z2 gets passed. Okay, so the shape of it is 4 by 64, and the full formula is, let's say attention is a function of query key value, then it is equal to softmax of q dot k transpose divided by root over dimension, and then dot multiplying by V matrix. Okay, so Q dot K, just a summary. Okay, Q dot K transpose is giving you the similarity scores. Remember, we got 1.7, 1.6, all those scores. Okay, and then we divide them with root over dk, or dimension of k, scale down to prevent softmax from saturating. Then we use the softmax function. We turn the scores into weights that sum to 1. Okay, then we got 0.43 and so on, and then we dot multiply with the value matrix, which gives us the weighted blend of actual content. Okay, so the mechanism, if we have to say it in one sentence, is this: for each word, compute how relevant every other word is to it using query and key. Remember the Q dot K transpose, right? That's the one. And then use those relevance scores to take a weighted blend of every word a word is actually offering, which is V. Okay, so the whole process, okay, in just one sentence. Let's say this is the final definition you needed to understand, and in the next video I'll explain multi-head attention. Goodbye for now.